And our next presenter will be Daniel Anthony Howard from the University of Southern Denmark. He will be presenting his paper identifying best practice melting patterns in induction furnaces, a data-driven approach using time series k-means clustering and multi-criteria decision making. The floor is yours.
Thank you. Yes, the mic. Okay, thank you all for being here, and I'm happy to be here to present the paper for best practice identification in induction furnaces. The background behind this paper stems from the industrial sector, accounting for approximately 40% of the current global energy consumption, and specifically within the industrial sector, the iron and steel industry is categorized as the one with the highest carbon dioxide emissions, where we specifically see that the melting portion of the iron and steel industry accounts for almost 55% of the energy consumption. The interesting thing about the iron and steel industry from a energy efficiency and flexibility point of view is that during the melting process, you can't really do flexibility in the process, because when you start melting the alloy, you are not really interested in lowering or changing the temperature profile. So therefore, the primary thing that you can try to optimize when it comes to the melting part of the induction furnace in a foundry is energy efficiency. So we can become better at actually melting our alloy. And therefore, it's all about the practices and how we approach melting in an induction furnace. It has been shown that the unfavorable operation of induction furnaces can actually lead to a 25 to 30% loss. So there is definitely potential for furnace operators to improve on the overall practice in the furnaces. However, currently the furnaces are operated by experienced people that have a lot of tacit knowledge based on their vast experience with the melting, something that is hard to kind of note down and to quantify. So therefore, we need a data-driven approach, and this is also necessary because there are so many different melting patterns when we look at induction furnaces, and it's difficult to categorize them at the moment. So therefore, in this paper, we aim to present a systematic method for identifying best practice melting patterns in induction furnaces to enable energy-efficient operation. Coming into the proposed methodology, we propose a four-step process where you start with the data preparation and separation of practices. You then do a clustering of operational practices based on the clusters that now contain specific practices in the furnace. You can then evaluate the overall performance of that cluster, and then using multi-criteria decision making, we can try to evaluate what is the best practice. And using multi-criteria decision making, we are able to potentially weigh different assets or parameters of the melt differently. So for the clustering part in this paper, we used time series k-means clustering, and we did this to identify similar practices in the production process. The neat thing about time series k-means clustering is that we can handle the temporal nature of the data, and it also, using this dynamic time warping matching, we can actually have data sets of varying lengths in our data, and that's especially important when you're dealing with an operational practice, because maybe one time the melt will take 60 minutes and another time it takes 70 minutes. So you are dealing with data sets of varying lengths, and in order to identify the optimal number of clusters, we used the elbow method for this. We then used multi-criteria decision making, and we employed a number of algorithms here, and as the literature suggested, this increases the overall decision robustness, so we can see how the preferred solution potentially varies across various algorithms. We used the SAW, mu, the TOPSIS, modified TOPSIS, and the VCOR method in this case. It should be said that these are, of course, decisions made in this case, but looking at the proposed methodology, you could take another approach for clustering, and of course you could also take another approach for how you evaluate use other multi-criteria decision-making algorithms. So in order to verify our methodology, we looked into a case study for an industrial foundry, and the foundry generally considers a melting part of a process. It considers a casting part and a machining part. So in the casting part is where you take the molten alloy and you shape it into some kind of object, and in the machining part you are doing like surface treatment and things to enhance the overall properties of the alloy. But in the melting part is where we find the most energy consumption, and in this part they use induction furnaces. This is a picture from the process where you can see quite a high temperature melting over here. And it basically functions by gathering metals and alloys. Some of this are from a scrap pit. And then they melt it in a furnace. And when the melt completes, they transfer it to a holding furnace using preheated transport ladles, so like a big metal bucket. And then they collect it for alloy casting and cast it into objects. In this study, we emphasize the melting in the furnace because this is where we find the most of the energy consumption and therefore maybe also the biggest potential for energy efficiency. So coming back to our proposed methodology, we start with the data preparation and separation of practices. So we received around 14 days of data from the foundry operator. And in this case, we had some data preparation to do because there was some missing data in terms of temperature, but also on the furnace state, which was not properly monitored. After doing the necessary cleanup here, you can see some of the data over here, how they operate the furnace throughout the 14 days, and I've zoomed in on some of the data here. And what we want to do at this part is now that we start to separate the melts. So we have these individual like spikes that indicates the completion of a melt. And then when you empty the furnace, it drops down, and we want to identify, basically separate out all these different spike melting patterns here. So we proposed a melting pattern identification algorithm, which basically use a minimum temperature change and a temperature limit. So we utilized the fact that when the melt finishes, there is a sharp drop in the temperature. And by identifying this sharp drop, by tuning our parameters, we can actually identify these various practices. Yeah. Then coming into the clustering after separating all the melts, we can see that we have separated the melts over here, and we used 12 clusters based on the elbow method. In this case, we were actually also able to identify some of the operational practices in the industry, because if you look at the purple line here, this is actually them changing the refractory lining in the furnace. So we can actually also, based on talks with the operators of the furnace, we were able to identify that this is a specific maintenance operation of the furnace. So there is maybe also potential in the future to identify and classify various actions within the process. Coming into the evaluation of the cluster performance, so the next step here, we have identified 12 clusters. Now we want to evaluate how each of these clusters generally perform. So we evaluate this based on production time, electricity consumption, energy-specific performance. So the energy-specific performance is an important KPI for the foundry, because this measures how much electricity they basically use per ton of melt. And then we included the 2030 carbon taxation, because after 2025, the Danish government has agreed to phase in a carbon taxation for Danish industries. So it will also become increasingly important how much carbon they're actually emitting in their process. So using these parameters and the values here, we do the multi-criteria decision making, where we evaluate all the different clusters. And based on the multi-criteria decision making, we could see that cluster 3 in this specific instance provides the best or the preferred solution in this case. And we are lucky because it provides the preferred solution across all of the multi-criteria decision making algorithms. Of course, you could be in a situation where this is not the case. then maybe you need to do multi-criteria decision making of multi-criteria decision making, or do some kind of like which one provides the best overall. So in this case, we identify 3 as what we consider the best practice operation from the data. And using this best practice, we then try to evaluate how does this perform operationally. So from an approximation, we could see that if they actually adhere to this best practice operation most of the time, they will be able to save around 8.6% on the overall total electricity cost, and this is factoring both the carbon cost and electricity cost in this case. So there is definitely potential for improving just using the best practice operation of the furnace. So coming to the discussion of this proposed methodology, we have applied time series k-means clustering for categorizing the melting patterns to identify various practices within an industry. We have calculated the performance parameters for each cluster to assess their efficiency and environmental impact. We deployed various multi-criteria decision-making methods to determine the best practice, and we evaluated the potential cost savings based on this specific practice. This also enabled, as I said, identification of specific operations within the furnace, so we could see this, like for example, the change of refractory lining in the furnace. And we also found that actually the melts adhering to what is considered best practice at the moment is only 12% of the time. So there's definitely potential for them to increase the number of times that they are doing best practice operation. So coming into the conclusion here, based on the case study and the furnace presented, this provides a methodology for doing data-driven identification of best practice operation. The neat thing, I think here, I've worked a bit with industries, and this uses realized operational patterns. So the data that we have analyzed is something that we know they are able to do because it's based on the historical operation of the furnace. So it's not some theoretical best practice we are providing them. We are actually providing them with a realized operational pattern that we know that they have been able to do, and then they could maybe try to be more adamant about continuing doing this. So the cost savings would be around 8.6% in this case. And some of the limitations and future work that could be considered for this is that currently we consider all melts the same, but we have different alloys in our furnace. So every time we start a furnace, we will have a different alloy composition that we are trying to hit. In this case, you could maybe be in a situation where you would try to do a best practice operation of induction furnace melting based on alloy composition. So there might be best practices for the various alloys in this case. Then, of course, doing this for multiple furnaces, we only covered one furnace in this study, but multiple furnaces and across multiple foundries would verify the generalizability of the methodology, and you could implement this best practice in a ditto twin to investigate the implications of best practice. So in this case, we did an estimation of how much savings they could get from the best practice. But of course, when you start changing your operational practice, it also changes the flow of products. It changes the maybe work scheduling. And to evaluate all of this, it would be ideal to create a ditto twin solution where we could evaluate these best practice operations and maybe actually do multi-criteria decision making based on the performance in the ditto twin. So the work here was sponsored by the Danish Energy Technology Development and Demonstration Program under 2 projects that you can read here. I provided a number of references throughout this slides. So if you if you are more interested in any of it, please feel free to look at them here. And also, of course, feel free to connect with me, reach out if you have any questions or would like to discuss. Always open. So yes, that was all for me.
Thank you, Daniel. So now we have time for some questions. Yes.
Thank you. Have you tried any other method than KMC to see if the result is different or not? Any other clustering method?
No, I actually haven't. I used the time series k-means clustering because there's a guaranteed convergence on that. But of course, you could try other clustering approaches. I think that's the good thing about the methodology, that how you clustering is not really defined. So if you have another approach, then of course you can do that. But interesting for future work, definitely, to maybe try to evaluate how different clusters, clustering algorithms would maybe change that result in the end. Yeah, definitely. Thank you.
Any other questions? Yeah.
Thank you for the nice presentation. I'm curious that could you please explain the difference of cluster 3 with other clusters in practice? Because in your results, it's just the number from 0 to 11, right? But could you explain the differences?
Yeah. So the differences is maybe I can see if I can go back. Yeah. Okay. So the differences here are, of course, how closely aligned in the operational, like how comparable they are. So they are not necessarily only for like the purple one where we're able to identify that it is like a specific practice, but the other ones are just ways that they have operated the furnace. And the reason why cluster 3 performed so well was that it is could say like short and good melt, where they just get the temperature up quickly and finish quickly. So therefore they basically get the melt done quickly, and they use less energy, because in some parts they will have a quality control, and if they don't meet the quality aspects of the melt, they will have to add some additional alloys, and then they will have to bring the melt up again. So depending on how good they are in the beginning, maybe that can be some of the reason why cluster 3 is performing better compared to the other clusters. I don't know if that.
Yes. Well, thank you very much.
And one last short question.
Yeah, thanks for a very, very nice presentation. I noticed that you said that you have the benefits of realized operational scenarios and so on. But very often when we try to do optimization, we do some experimental design to ensure that things are not confounded and ensure causality, and maybe we can also identify new operational areas or a mix of effects which has not been taken into account, and I can mention logics. Can you elaborate a little bit on why you have you considered the other alternative, or why did you exclude that? Was it impossible? Yeah, I will stop. Thanks.
Maybe you can elaborate a bit on the question, Henrik. I'm not sure I completely understand what you mean.
No, but we have a lot of cases where we had, for instance, on waste incinerator plants, where we have found out how to optimize the output and minimize the production of dioxin and things like that. And of course, they operate in a specific way. But what we do normally then, and where we have gained a lot of advantages and improvements, is we tell them to operate in corners of some experimental design in a random combination so we ensure that we have a causality, so we know what is causing what, for instance. But of course we can discuss that maybe over the lunch or something. I can, but I also understand that it's could be an advantage to take into account or to do it the way they operate normally. But I think there are pros and cons.
Maybe what I can say there is that from my personal experience with the industries are that they are generally a bit hesitant to just blindly trust what I come and say, like, I do like this. So I feel like it was a better selling point saying, this is actually something that you have already done. So if you can just do more of this, then you can improve without having to operate in corners that you have not been in yet, maybe. So yeah, but I would love to discuss further. Yeah, definitely.
Thank you all. And thank you, Daniel.